This video is on one of the most useful derivative rules, which is called the chain rule, or TCR for short. To introduce the chain rule, I'm going to look at a special problem. So we know that the derivative of sine of x is positive cosine of x. And we also know that the derivative of 2x is simply 2. But what is the derivative of sine of 2x? Well, we don't know yet, but with the chain rule we'll be able to answer this question. And the chain rule is nice because now we can figure out how to take derivatives with composition of functions, which are the most common functions that show up everywhere, basically. So here's like the definition of the chain rule. In order to find dy dx, we're going to have to go through a middleman, which is going to be u. So we're going to do dy du times du dx. This is one way to look at it. I don't personally like this way because it's kind of complicated, because you're like, what's u? And that's kind of weird. Another way to look at this is like this. You have f of g of x with lots of colors for your parentheses, and we're taking the derivative of this. Okay, and the way we take the derivative is we work outside to inside. So when we do this derivative, well, the derivative of f is just f prime, and then the main rule with the chain rule is that the stuff inside stays the same. So it's f prime of g of x, and then once you do that, then you take the stuff inside and you multiply this times the derivative of the inside stuff. So you take f prime of g of x, multiply by g prime of x. And honestly, you can continue this process until you run out of variables, basically. So we'll look at some examples if you need to keep using the chain rule and when to stop. So let's go back to this original problem. When I do the chain rule, I like to think about eggs. Yeah, kind of weird, but that's okay. And so I like to think about this problem in terms of not the derivative of sine of 2x, but instead the derivative of sine of stuff. Okay, because you have stuff inside eggs. And so the way the chain rule works is you, like an egg, or maybe an onion, or maybe an ogre, you start at the outside layer. The outermost layer of this is sine. So we take the derivative of sine. The derivative of sine is cosine. Great. So derivative of sine goes to cosine, done. Now, the stuff inside stays the same. When you peel off the first layer of your onion, the inside stuff is still the same. Then you peel off the next layer. Okay, so the next step is, after you've done the derivative of sine, is to do the derivative with respect to x, or whatever variable is, of the stuff. Okay, so you're peeling off layers, and as you do so, you're taking derivatives. But when you do that, you need to make sure that the stuff inside stays the same for each level. So we have this problem, sine of 2x. Well, the derivative of sine is cosine. Great. Hey, the stuff inside, the stuff is 2x. That stays the same. You need to keep that as 2x. And then you need to take the derivative of 2x. Now, this is important, and I want you guys to do this. It might seem ridiculous and repetitive, but it's important, and you'll find out why in a few sections. When you take the derivative of 2x, I want you to write 2, because that's what the derivative is according to the power rule. But then I want you to go one step further, and we took the derivative with respect to x. So I want you to write dx dx. Okay? Because essentially you're doing the chain rule again, where you're saying, okay, the derivative of 2x is 2 times the derivative of x with respect to itself. Okay? So I want you to do that when you're doing these chain rule problems, and all derivatives in general, until we reach a certain point in the material. And I'll tell you when that is, but don't worry. So we have cosine of 2x, and guess what? That 2 dx dx popped out. Guess what? Dx dx is 1, because it's like the same thing over itself. This turns into a 1 and goes away. So we're left with cosine of 2x times 2. You can rewrite this, if you like, as 2 cosine of 2x. Like that. Yay. Really, that's all the chain rule is. It doesn't seem that hard at first, but then you start looking at problems and it gets a little bit more tricky. So let's look at some examples just to show you guys what's out there. This is a nice problem that could be done in two ways. The first way is we could expand this out because it's only a cubic, so we have like x squared plus 1 times itself 3 times and go from there and then do each term separately. That might take a while, so let's try this using the chain rule. You need to get good at identifying the layers of functions. So here we have one layer of function, which is the function cubed. I'm going to redraw that in red. And then the other layer of the function is simply just the stuff in black on the inside. It's not multiplied, or there's no more layers of functions because there's nothing else going on other than x squared plus 1. So when we do this, we do each layer individually. The first rule is a power rule. How do we do the power rule? Well, we bring down the 3 in front and we subtract 1. So I encourage you to think about it like this. We have stuff cubed, so the derivative of stuff cubed is 3 stuff squared. Great. Now ask yourself, what's the stuff? Well, the stuff inside is the x squared plus 1, so we're going to write that in. Are we done? No, because now we need to chain rule this. You know we're done when there's no more layers, essentially. So we chain rule this, and we get the derivative of the derivative of x squared plus 1, which is 2x. And now this is that kind of awkward next step. Okay, the derivative of 2x, no, I don't want to do this. Sorry, got a little bit confused. Okay, that last step, that kind of like dx step, you're really just taking the derivative, like the next quote-unquote inside function is just the x itself. So like the last step of the chain rule that I'm making you do right now, but you won't have to do forever, is to write dx at the end. Okay, so your final derivative looks like this. 3 x squared plus 1 quantity squared. And then on the we also have a 2x here, so times 2x. And remember that dx, it does become 1, so then we can get rid of it, but I want you to write it. I'll explain why when we get there. And so this is your answer here, and you can multiply that to become 6x x squared plus 1 squared. And really the chain rule is kind of nice, because it's a manageable derivative process. We'll do a harder example that has a little one more step. So let's say we have the square root of sine of 3x to the 4th. And because this is calculus, we're going to differentiate it, because that's what we do in calculus. But in order to do that, I need to figure out what the outermost function is. Well, here it looks like it's that square root thingy. How do we take this derivative of square root? Oh, we should rewrite this as an exponent, because we can do that with square roots. Remember all those silly things you learned in Algebra 2? They actually work here in calculus. So we're going to rewrite it. It's sine of 3x to the 4th, quantity, all of that to the 1/2. Remember, square roots become a 1/2. And now, this is nice. We have one rule, which is an outside power rule. We have the next rule, which is the sine, and then the innermost function, which is the 3x squared, or 3x to the 4th. So we do it in order. The first rule is the power rule, so I bring down the 1/2 stuff to the negative 1/2. What's the stuff? The stuff is the inside, so it's sine of 3x to the 4th. Do not change that, it hasn't changed. Right? Then I have sine, and I have 3x to the 4th. Well, now I do it again. The next derivative is going to be the derivative of sine. Sine goes to cosine, so I have cosine of stuff. What's the stuff? The stuff is the 3x to the 4th. I haven't changed it because we haven't gotten to that layer of the function yet. Now we're at that layer, and so now I'm going to take the derivative of 3x to the 4th, and that derivative is a straight power rule. I'm going to get 12x cubed, and then technically again, there's that last awkward derivative at the very end there with the x, and that's going to give us our dx, okay? And then, great, dx, that immediately becomes 1. And then we can simplify everything. So let's combine all the constants. We have a 1/2 times 12, which is 6. Let's see, we have a cosine of 3x to the 4th, or we have an x cubed. There we go. We have a cosine of 3x to the 4th on top. And on the bottom, because it's a negative exponent, and it's a 1/2, we'll have a square root of sine of 3x to the fourth. So is the derivative of a 3 nested function thing kind of nasty? Yeah, it's a little bit nasty. We got some fractions and square roots and trig, but that's okay. We can deal with it because we're calculus pros now. Last example I want to look at is an alternative to using the quotient rule only in some cases. And that happens when, bam, you just have a constant up in the top. And the way this is going to work is we're going to rewrite this function so that everything is in the numerator. So we have negative 7, and then all I'm going to do is bring this up by making the 2 a negative 2. I can do that because it's math, and I can do anything. So we change the function like that. Now I can take the derivative using the chain rule, and it's going to turn out to be rather easy, at least easier compared to the the quotient rule. My outermost function, hey, ignore that 7. Anytime you have a constant that's multiplied, ignore it, because you'll just end up multiplying it back in eventually. So my outermost function is really this negative 2, and it's an exponent. How do I take the derivative of an exponent? Well, you're going to bring it down in front and multiply it with that constant. So we're going to get a positive 14 stuff. Remember, you're subtracting 1 here, so that's going to be a negative 3. Oh, what's my stuff? My stuff is 2t minus 3. Great. Now I'm going to take the derivative of 2t minus 3, and I'm going to get 2 times dt dt. There it is. And guess what? dt dt is 1, so it goes away. And now I'm going to rewrite it in our final answer form. So 14 times 2 is 28. This is a negative exponent, so I'm going to put it back in the bottom. So it's going to be 2t minus 3 to the third. And that's all for now. Enjoy.